Quantum computers leverage quantum bits, or qubits, which can exist in multiple states simultaneously, unlike classical bits. This property, known as superposition, allows quantum computers to process complex calculations at unprecedented speeds. Additionally, quantum entanglement enables qubits to be interconnected, enhancing computational power. These principles form the foundation for quantum software development, paving the way for languages like Q#. Quantum languages like Q# are pivotal in quantum software development. Q-number is designed for expressing quantum algorithms and integrates with classical languages. It supports quantum operations and data structures, facilitating the development of quantum applications. Understanding these languages is crucial for leveraging quantum computing's potential in various fields. Quantum computing leverages superposition and entanglement, enabling parallelism beyond classical computing. It promises speed-ups in quantum chemistry, materials science, cryptography, and machine learning. The qubit, existing in superposition, forms the basic unit. Quantum operations, or gates, create circuits, fundamentally differing from classical binary systems and Boolean logic. Quantum programming languages address the limitations of existing high-level languages by providing constructs for meaningful quantum computations and quantum classical logic. They abstract low-level concerns like error correction and noise, essential for quantum devices. These languages facilitate the interaction between classical and quantum logic, treating quantum computers as adjunct coprocessors rather than standalone devices. The evolution of quantum software has shifted from circuit descriptions to algorithm definition languages. Early languages struggled with expressing complex quantum algorithms involving classical control and recursion. This led to the development of languages that utilize intermediate representations, enabling more sophisticated quantum program execution beyond static circuits. Q-number is a high-level, domain-specific language by Microsoft, integral to the Quantum Development Kit. Unlike circuit-based languages, Q# is an algorithm definition language, emphasizing clarity and completeness in quantum algorithms. It supports classical determinism, first-class callables, and qubit-type opacity, integrating with Visual Studio, Azure Quantum, and Jupyter Notebooks. Q-number is built on core design principles that ensure robust quantum programming. Its type system guarantees correctness and safety, while a tightly constrained environment interleaves classical and quantum computations. The specialized syntax and symbolic code manipulation, like adjoint transformations, enhance algorithm expression. Functional constructs and the quantum random access memory model support complex algorithm composition and efficient qubit management. Q-number distinguishes between operations and functions to maintain clarity in quantum programming. Operations can alter quantum states and integrate classical computations, serving as the core of Q# programs. Functions, however, are purely classical, ensuring consistent outputs without affecting quantum states. This separation enhances deterministic reasoning in classical computations while managing quantum effects effectively. Q-number provides classical primitive types like int, double, Boolean, string, and range, essential for quantum algorithms. Quantum primitives include poly for measurement bases, result for measurement outcomes, and qubit for representing quantum bits. Notably, Q treats qubits as opaque, focusing on state transformations rather than direct state representation. Q-number manages qubits using a heap model, allocating and releasing them as needed. The use statement allocates clean qubits, ensuring they are reset to 0 before release. The borrow statement uses dirty ancilla qubits temporarily, returning them to their original state. This stack-like memory management prevents double allocation or release, enhancing resource efficiency. Q-number offers classical flow constructs like for loops for iterating over ranges and if-elif else for conditional logic. Unique to Q-number is the repeat until fix-up loop, enabling the repeat until success pattern. Variable bindings include let for immutability and mutable for changeable variables, with set to update mutable values within their scope. Q-number operations can specify adjoint and controlled variants using characteristics like adj and CTL. The compiler often auto-generates these, performing symbolic computation on the operation's body. The controlled variant applies operations based on control qubits' states, crucial for algorithms like Grover's search, which iteratively applies an oracle. Partial application in Q# enables runtime creation of new operations by providing a subset of parameters, leaving others unspecified. Unlike currying, any parameter subset can be left out. This doesn't affect the quantum state, facilitating new operation construction. Generics in Q# allow type parameterized operations, supporting unresolved generics as first-class types, enhancing flexibility. Debugging quantum programs is complex due to probabilistic measurements and vast state spaces. Qer aids with the message function for diagnostics and assertions like assert and assertprob for expected outcomes. On simulators, assertions can measure without state disturbance, providing robust checks, while on hardware, they return without effect. The random bits operation in Q generates random bits by allocating n qubits, applying a Hadamard gate to each and measuring them. This process creates a superposition, resulting in a 50% chance of measuring 0 or 1. The results are stored in a mutable array, and qubits are reset to ensure safe deallocation. The Q-number example demonstrates key quantum programming concepts: allocating qubits, applying Hadamard gates for superposition, measuring in the z-basis for randomness, and resetting qubits. This process yields random outputs like 0, 1, 0, 1. Project Q offers similar functionality, highlighting shared patterns in quantum programming across various frameworks. Quipper, a functional quantum programming language embedded in Haskell, excels in scalability and algorithmic complexity. It uses quantum random access memory for quantum operations and introduces QC data for quantum information, leveraging Haskell's type classes. Quipper supports higher-order computations, sending gate-by-gate instructions to quantum devices, showcasing the power of functional languages in quantum programming. Quipper, a functional quantum programming language embedded in Haskell, excels in scalability and algorithmic complexity. It utilizes quantum random access memory for quantum operations and introduces QC data for quantum information, including qubit and bit types. Quipper supports higher-order computations, enabling functions as data, and sends real-time gate instructions to quantum devices. Project Q is an open-source framework embedded in Python, designed for ease of use and extensibility. It supports various backends for resource estimation and circuit drawing. Utilizing Python's garbage collection, it efficiently manages qubit deallocation. Its high-performance C++ simulator accelerates execution, enabling algorithms like Shor's and quantum teleportation with comprehensive examples and documentation. Silk, developed at ETH Zurich, is a high-level language designed to simplify quantum programming. Its powerful static type system minimizes errors through early verification. Silk treats quantum states and measurements intuitively, enhancing algorithm design efficiency. It also automates qubit management, reducing programming errors and streamlining the development process. Qiskit, developed by IBM, is a pivotal open-source Python library for gate-based quantum programming. It allows users to simulate and execute quantum circuits, primarily exporting code in open quantum assembly language format. With its extensive modules like Qiskit Aqua for optimization and machine learning, it offers flexibility, making it a favored tool among researchers and developers. Quill from Rigetti supports a mixed classical quantum memory model. QCL, similar to C, allows quantum classical computation interleaving. Q language extends C++ for quantum gates. Cirq by Google targets noisy intermediate-scale quantum computers. Liqui is embedded in FHIR, while Scaffold aids in quantum program compilation within C++. Quantum software faces significant challenges. Designing algorithms is complex due to superposition and entanglement. Testing is hindered by slow simulations and the risk of state collapse. Hardware limitations include low qubit counts and poor fidelity. There's a talent shortage, and development environments need advancement to meet next-generation demands. Timing sensitivity further complicates experiments. High-level abstraction in quantum computing is crucial for addressing programming complexities. The classic platform exemplifies this by using a patented synthesis engine to automatically generate optimal quantum circuits from high-level specifications. It allows teams to focus on desired algorithms, adapting to hardware constraints, and interfacing with compilers like Qiskit, QNumberSign, and Cirq. OpenQASM is evolving with features like unitary circuit families and classical arrays. QNumber is enhancing resource management and debugging tools. LQPOW aims to provide a robust mathematical foundation. Microsoft's QIR, based on LLVM, is formalizing high-level to low-level compilation. Hardware-software co-design is crucial for optimizing quantum performance. Quantum programming languages are evolving rapidly, addressing unique computational needs. Open Quantum Assembly Language and Q# exemplify this, with Open Quantum Assembly Language focusing on low-level control and Q# on high-level abstraction. Diverse languages enrich the ecosystem, while higher abstraction levels and integration efforts are crucial for advancing quantum computing's potential. Thank you for your attention.